Yes, I have started it.
Yeah, yeah. Okay. Yeah. So hi, I'm Avinandan. So I was a bit confused about what to talk in this uh, group talk. First, I thought that I would talk about my primary research topic, which is on statistical mechanics of self-gravitating systems, which is in itself a very non-trivial problem because once you bring long-range forces like gravity into picture, various non-trivialities develop in even in simple statistical mechanical systems. But then I thought that maybe for a short talk, this topic on higher dimensional partitions would be better suited because the problems that I will talk about here are very simple to state. In fact, it is true for every problem in discrete mathematics. Like even if you think even if you see the problems on graph theory that Avni spoke about last week, they are very simple to state problems, but they're incredibly difficult to tackle and to prove. So this is also one of those kind of problems that I will discuss on. Uh, and so first of all, why should we bother about partitions? First of all, it is an interesting problem, and this reason is enough for mathematicians to embark on this problem. But we as physicists are also interested in this problem because of many reasons, like the ones I have stated here. I have stated it in quotes and unquotes because I'm not aware of any of these applications right now. Like it is being used in Potts model, which I have, like it is a generalization of lensizing model of magnetism. Similarly, it is used in string theory or in many other areas of theoretical physics. However, my talk will be more on the mathematical aspects of it, not on its use in physics. But surely it has lots of physical applications. I hope to learn about those applications in future for sure. And if I give any talks in future, I will talk about them, of course. And so before beginning with higher dimensional partitions, we first have to understand what is ordinary partitions, or the so-called one-dimensional partition of integers. So, okay, by the way, if you have any doubts or anything to ask in the middle, just interrupt and ask, okay? Because I can't see the meeting screen from here. By the way, I'm still audible and everyone is with me, right? And the screen is visible.
Yes, you are audible. Yeah.
Oh, yeah, yeah, okay, okay. Fine. So if you have any questions, just interrupt and ask. So yeah, so I will start. I will start with one-dimensional partition of integers. The basic idea is very simple. For example, if we take a number, let's say 5, then 5 can be written out as 5 plus 0, or as let's not keep it as 5 plus 0, 5, or as 4 plus 1, or as 3 plus 2, or maybe as 1 plus 1. Yeah. So one-dimensional partition of natural number n is a weakly decreasing sequence. Weakly decreasing means it is not strictly monotonically decreasing, uh, but it essentially means that ai plus 1 must be less than equals to ai. It can be equal. So one-dimensional partition of natural number n is a weakly decreasing sequence of non-negative integers such that the sum turns out to be n. And of course, the sequence has a finite support. I mean that uh, the rest of the terms will be 0. It has to be if n is a finite number. And the number of such partitions of n is called the one-dimensional partition function of n. Don't confuse with the partition function of statistical mechanics here. It is called the 1D partition function of n, and it is denoted by P of n. For example, of course, we can compute some simple partition functions like that of 3 will be just 3, 2, 1, 1, 1, 1. And yeah, that's it. So P of 3 will be 3. And so now let us try to visualize these partitions from a a bit different perspective, and that is the perspective of Ferret's diagrams. So what is a Ferret's diagram? So let us take one example. Let us take the partition. Let us take this partition of 5, which is 5 equals to. Let's take a bit bigger number. Let's take 10, and consider this partition 5 plus 3 plus 2. What you can do is we can write this partition as 5 dots in the first row, then 3 dots, and then 2 dots. So this is 5, this is 3, and this is 2. The total number of dots is equals to 10. So a Ferret's diagram of a partition of a natural number n is a collection of integer lattice points in the real plane. In the real plane's first quadrant, I mean, if I take this to be the x1 axis and this to be the x2 axis, I mean our axis rotated by 90 degrees, nothing more than that. And so a Ferret's diagram is a collection of points in Z2 greater than equals to 0. I mean, the first quadrant of the R2, where we consider only the integer points, such that now this will not be a partition of 10. For example, this has 4, this has 5, this has 1. Still they add up to 10, but you can see that the sequence is not weakly decreasing, because after 4, 5 comes, and 5 is greater than 4. In fact, if you look at it, the main reason behind this weakly decreasing criterion is that we don't perform a overcounting, because if I allow both this to 1, 1, 1, as well as 1, 2, 1 as a partition, then it will just overcount this partition twice. So to prevent that overcounting, we need to bring this criterion of weakly decreasing nature. And coming back to this is not a Ferret's diagram of a partition of 10, because to us 4 plus 5 plus 1 will not serve as a partition of 10, but 5 plus 4 plus 1 will do. So this is not an acceptable Ferret's diagram. So just an arbitrary collection of points in the two-dimensional lattice plane will not work. So we must have to bring an extra condition such that it respects the weakly decreasing nature. And that extra condition is actually quite trivial. If you take this point in your Ferret's diagram, then you must have to take all the points that are lying inside it. Then only it will satisfy a weakly decreasing. It will satisfy the weakly decreasing criterion. And so if I stated it here. Okay, let me just be precise. So we will have a Ferret's diagram of a number n. If it is a collection of n many points in Z2 greater than equals to 0, I mean the first quadrant of R2, where we are considering only the lattice points, such that if A1, A2, this point belongs to this Ferret's diagram, then is there any problem? And x1 x2 must also belong to the Ferret's diagram, where 0 less than equals to x1 less than equals to a1, and 0 less than equals to x2 less than equals to a2. This criterion essentially takes care of the fact that the sequence must be of quickly decreasing nature. So this definition of partition can be equivalently formulated in terms of Ferret's diagram, and this is as follows. A 1D partition of a natural number n is a collection of n many points in the first quadrant of the lattice plane, such that if a1, a2 belongs to the partition, then so must belong x1, x2, where x1 and x2 lie between a1 and a2. And in fact, this definition of partition in terms of Ferret's diagram is very, very useful, and it readily generalizes to higher dimensional partitions, as we shall see. Now, another important application of Ferret's diagram is proving various partition identities. For example, uh, consider consider a partition identity like this. Let us suppose consider the partition of n, where n is a natural number, such that n has n many, such that the partition has n many parts. So what do you mean by that? It means that we consider a partition of n equals to n1 plus n2 plus, such that the number of parts is n. So this number is equals to m. So partition of n with n many parts, so it is a restricted partition. We have some condition on the partition. This is equals to partition of n minus m, such that each partition has at most n parts. So relations like these are called partition identities, which are relations among two restricted partitions. And if you are not introduced to Ferret's diagrams, then proving this partition identity may be difficult for you. In fact, you won't have any idea about how to approach the problem. But once you have the interpretation of one-dimensional partitions as Ferret's diagrams, then proving this is trivial. I mean, extremely trivial. Consider a Ferret's. So what we do is, in proving these kinds of identities, we take this set S1 to be the set of partitions of n such that it has n many parts, and the set S2 to be the partition of n minus m, which has at most n parts. And then we prove a bijection from the set S1 to S2. If a bijection exists from the set S1 to S2, then clearly the cardinality of the two sets should be same. And of course, they're finite sets, so bijection proves that the cardinalities would be same. And this bijection is a Ferret's bijection. We don't write down an explicit mathematical function between S1 and S2, but rather we prove a diagrammatic way in which one Ferret's diagram can be transformed to another Ferret's diagram. And we that this transformation can be uniquely reversed. So let us look what bijection shall prove this partition identity. So consider a partition of n which has n many parts. So the number of rows will be n. And then what we can do is we can remove the first column. Once we remove the first column, it will still remain a partition, as you can easily see. It will still remain a partition. But now it will be a partition of n minus m, because you have removed n many points from here, so there are n minus m points left. So it is a partition of n minus m, and the number of rows that you have now is less than equals to n minus 1. Sorry, number is less than equals to n, as you can clearly see, because it has n many rows. After removal, it cannot have the next column cannot have n plus 1 rows, because then it will violate the condition of Ferret's diagram. So if the first column has m rows, the second column must also have m rows. And this is nothing but the second column, which has become the first column now. So it will have at most m rows. And now this transformation f can be reversed uniquely by just putting a row of m many points in before. So if I put a row of m many points before this partition, it will still be a partition, and it will be a partition belonging to this set S1. So this partition belongs to set S1, and this partition belongs to set S2. And there is a unique bijective function or a bijective transformation that maps an element of S1 to S2 and back from S2 to S1 through F inverse. And thus, this will serve as a bijection, and hence the sets cardinalities are same. And this cardinality of set S1 is nothing but this partition M, this restricted partition M. And the cardinality of this set S2 is this restricted partition, and hence both of them are equal. And this is just one of the most trivial partition identities. In fact, you will be amazed to see how extremely non-trivial partition identities, in which you won't even have an idea about how to approach the problem, can be solved very easily just by playing with the Farre's diagrams. So it is one of the it is a very beautiful thing to see. However, I won't be talking about more partition identities right now because I have to get to higher dimensional partitions. So now I will start with generating functions. Now, generating functions, I think this word is familiar to most of you who have done any course on special functions and orthogonal polynomials. And the main idea is essentially still the same. So let us suppose, so to motivate the idea, consider consider n less than equals to 7, and a set S1 to be say 2, 4, 6, and the set S2 to be say 1, 3, 5. That is, S1 is the set of all integers, all even integers less than equals to 7, and S2 is the set of all positive even integers less than equals to 7, less than 7. And consider partitions of n such that the partition has two parts. Partition of n such that the partition has two parts. That is, n is written as a plus b, two parts, such that the first part, let's say n1, n1 plus n2, such that n1 belongs to set S1 and n2 belongs to the set S2. And let us keep 0 also in these two sets. So now consider this 1 plus q square plus q to the power 4 plus q to the power 6. And 0 can be considered an even, not an odd. So let us remove 0 from here. Okay. q1 plus q3 plus q5. And now if you perform this addition, if you perform this multiplication, what we will have q to the power 2 plus 1 plus q to the power 4 plus 5, q to the power 6 plus 1, q to the power 6 plus 3, and q to the power 6 plus 5. Now let us look at, let's say 5. Let us put n equals to 5. And let us see where did the exponents 5 come. So 1, 5 comes here, 1, 5 comes here. And there are no other 5s. So this will be 2 times q to the power 5. For n equals to 3, the exponent comes only once. So it will be q to the power 3. Let us put n equals to 7. And we see that the exponent comes twice. So as we will see that the terms in the exponents actually contain all possible ways in which you can obtain the respective n's out of these two sets S1 and S2. So if I take, let's say, so I can write this identity, summation of n equals to 0 to infinity, partition of n with two parts. The first part n1 belonging to the set S1, and the second part n2 belonging to the set S2 is equals to q square plus q to the power 4 plus q to the power 6 I'm sorry, times q to the power n is equals to this times q1 plus q3 plus q5. And we have already verified it. I first took n to be less than equals to 7, but I think it is not needed because anyways, n can maximum go to 11 here. So the rest of the coefficients of n greater than equals to 12 will be 0 both in this side and in this side. So this is the partition identity. So this is the generating function for this partition. What is the use of generating function? Enumerating these partitions can be difficult. Well, for here it is easy because these are two very trivial sets. But if these two sets are very complicated sets or have large number of entries, then enumerating the partitions and calculating the partition function can be difficult. But once you have a generating function for this like this, you just have to compute the coefficient before the appropriate exponent, and that will serve. So this is so finding the generating function is one of the most important things if you want to deal with any partition problem. But sadly, for most of the partition problems in higher dimensions, generating functions don't exist, as we shall see. Here, in one-dimensional partitions, the principal problem is to compute P of n for large n. For small n's like n equals to 1, 2, 3, etc., let's say even up to 10, we can compute by hand. But computing Pn for large n, yes, we do have an algorithm. Like I myself developed one algorithm. I may be able to show right now, but well, I will tell later if I have time. But if you want to calculate it by hand, not by using any computer, or maybe you want a more efficient algorithm, then the only way you can do it is by finding a generating function for that. And as with many areas of mathematics, the generating function for 1D partitions was given by Euler, and the generating function is this. How do you get this generating function? Very easy. Let's see. So, what is the right hand side here? The right hand side is nothing but 1 times 1 plus 2 plus 2 1 plus 1. You'll understand why I'm keeping it 1 plus 1 and things like that. Times 1 plus this one plus 3 square plus 3 to the power 2 plus 2. And so on. This is the geometric progression, and this will give you 1 by 1 minus q. This geometric progression will give you 1 by 1 minus q squared, and so on. And each of these terms are multiplied. And that thing is essentially the right hand side. And as you can see, if you multiply these infinitely many terms, you will get all possible combination of these numbers in the exponents, and that will give you a ultimate partition function. So yeah, this thing I can't explain you much better right now, but you have to see it for yourself that this actually works. And this will give you the required partition function in 1D because in the exponent you will get all possible combinations that you need. So for example, if you want to calculate P of 3 from here, so you need to find out the exponent, you need to find out the coefficient of Q cube. And now let us look in the right hand side where Q cube comes. So Q cube comes once when 1, that is Q to the power 0 essentially. Let's keep it like this. So when will Q cube come? Q cube will come when Q to the power 0 will get multiplied to Q to the power 0 here also times Q to the power 3 and then rest of Q to the power zeros. Plus it will come once when Q to the power 1 here gets multiplied with Q to the power 2 here and rest all Q to the power zeros. Then it may come when Q to the power 1 gets multiplied with Q to the power 1 here and then gets multiplied with Q to the power 1 and rest all Q to the power zeros. And that's it. If you have three many possible entries, and thus the coefficient will be 3, and that is nothing but the partition function of 3. So that's how this generating function method works. It is a very powerful method, very powerful method. Uh, I can't just overestimate its power right now. And so let us now generalize all our techniques to higher dimensions. So what we had in a one-dimensional partition, we had a sequence n1, n2, all the way, and this sequence was weakly decreasing. That is, ni was greater than equals to ni plus 1, and the summation was equals to n. This partition we were calculating. Now we can generalize this idea to higher dimensions. So a d-dimensional partition of a natural number n is a d-dimensional hypermatrix, which is nothing but a d-dimensional sequence. So in 2 dimensions, it will be a normal matrix n11, n12, then n21, n22, and then n31, n32, and so on. So it is a d-dimensional hypermatrix which has non-negative integer entries. That is, these entries are non-negative integers, as was the case with 1D partitions. And this matrix is weakly decreasing along all the d dimensions. That's what this means. And the summation of all the entries is equals to n. So this essentially means that if you have a, let's say, 2-dimensional matrix, that is, we are considering a 2-dimensional partition. You have a 2-dimensional matrix like this. I mean, it's extended to infinity in all the directions. This box and this box, I mean, the entries in this box must be less than equals to the entry in this pink box. Similarly, the entries in this green box and this green box must be less than equals to the entries in this pink box, and so on. Essentially, it is weakly decreasing in this direction, in this direction. That's what it means. That's what I mean by partition in 2D. And similarly, it can be extended in 3 dimensions. So in 3 dimensions, it will be a 3-dimensional matrix, like an infinite cube, and it will be weakly decreasing in all these 3 directions. So the largest entry will be in this edge of the cube. And this can be extended to any higher number of dimensions. Now, as I have said, that Faraday's diagram gives you a very beautiful way to generalize partitions to higher dimensions. So here is one way in which you can equivalently define a partition in d dimensions. So just like the case of 1D where we had the corresponding one-dimensional partition has a corresponding 2-dimensional Faraday's diagram that is in the lattice plane. Here we have the Faraday's diagram corresponding to a d-dimensional partition in the d plus 1-dimensional lattice space, such that if this node belongs to the partition, then all other nodes belong to the partition which lie in the cube formed by that node. What I mean by that is simple, just like the case in 1D. For a 2-dimensional partition, the corresponding Faraday's diagram will be in 3 dimensions. So in these 3 dimensions, where this is the x1 axis, this is the x2 axis, and this is the x3 axis, if this node belongs to the partition, then all the nodes, by the way, these integer lattice points are also called nodes. So if this node belongs to the partition, then all the nodes which lie inside this small cube will also belong to this partition. And this again takes care of the fact that the partition, when written in terms of integers in d dimensions, it is weakly decreasing along all the d directions. That thing is taken care of by this requirement. And now, as was the case with 1-dimensional partitions, enumerating d-dimensional partitions is a very is one of the most important jobs when you are dealing with partition problems. But unlike the case of 1D where we have a generating function, and we have simpler algorithms. In fact, I may talk about. Do I have time to talk about it? Okay, I will talk about it later. That if you look at one-dimensional partitions, they satisfy a very simple recursion relation, and because of that recursion relation, well, it is not as simple as the recursion relation of Fibonacci sequence or like that, but there is a recursion relation in terms of restricted partitions, and that actually helps you to enumerate partitions of larger numbers in terms of some sorts of restricted partitions of smaller numbers. And that idea is what I use in my algorithm to calculate one-dimensional partitions. But it is very simple, and in fact, it is a well-studied problem. But partitions in higher dimensions, maybe in dimensions greater than equals to 3, even partitions in 2 dimensions, which we call plane partitions, is also well-studied, because even 2-dimensional partitions have a generating function. But as we shall see, partitions of dimensions greater than equals to 3, that is solid partitions and higher, they don't have a generating function. And so enumerating higher dimensional partitions is remarkably difficult. And in fact, this partition of 72, the solid partition of 72, it was enumerated by S. Balakrishnan, he was a undergraduate student at IIT. And this partition function evaluation, he used a extended version of something called Knud's algorithm, and it took a long time. It was an extremely computationally intensive job. And in fact, to the best of my knowledge, I think solid partitions up to 72 is known till now. I don't know if more numbers are added, but since we don't have an idea about generating function in 3-dimensional partitions and higher, computing solid partitions and 4-dimensional partitions or so on is extremely difficult. And you need to apply brute force algorithms, which actually enumerates all those partitions to calculate it. For example, to compute this partition function, what he had to do is he had to enumerate all these partitions. But if you look at partitions in 1D, they have to compute, let's say, partition of 895. You don't have to enumerate all the partitions of this number. You just have to compute the coefficient of 3 to the power 895 in the right-hand side expression. Well, it may be difficult, but can be handled without even enumerating all these partitions of 895. And enumerating these partitions will consume a lot of memory in your computer, and it will also need lots of time. And that will be a wastage of resource. And so generating functions are important in that sense. But since for 3-dimensional partitions, we don't have a generating function, so a brute force enumeration of all those partitions was needed to compute the number of partitions. And that's why it is computationally intensive. And yeah, what I was saying is about generating functions. So generating functions in 2 dimensions is known, and it is just a like in 1 dimension, the generating function was this. There was -1 here, -1 has to be replaced with k. This generating function was obtained by Percy McMahon. He was a major in British Army first, and then he became a mathematician and one of the most famous mathematicians in combinatorics in the last century. In fact, it was his idea to actually bring in high dimensional partitions. So previously, we just knew about 1-dimensional partitions. He extended the idea to arbitrarily large number of dimensions. And he came out with this generating function formula for 2-dimensional partitions. And the proof of it is non-trivial. I can't prove it right now. In fact, I also have to see the various nuances in the proof to reproduce the proof, but it is not as simple as partitions in 1D. And he actually used some ingenious motivation to conjecture that partition in arbitrarily large number of dimensions, I mean, in let's say any d dimensions, the partition function will have this generating function. And as you can see, like you can put d equals to 1 or 2 here and see that it reproduces the well-known and the well-proven results descend this. But this conjecture sadly has been proven false for d greater than equals to 3 and n greater than equals to 6. So till now, we don't have any idea about partition functions about generating function of partition functions in 3 and higher dimensions. And it is widely believed that maybe solid partitions, that is partitions in 3D and higher dimensions, may not have a simple generating function like this or this. However, it is still a conjecture to prove that no such generating function will exist. Well, so one of the main uses of generating functions is enumeration of the partitions and finding the partition function. Well, not enumeration of partitions, just finding the partition function. But another important use of generating function is to find the asymptotics. That is, how PD of n behaves for large n. Right? What will be its behavior as the power of some n to the power something, n to the power q, where q has to be found out, or as some power of log n, or maybe exponential of n. We don't know. We have to find out these coefficients. So this asymptotic in the limit as n goes to very high numbers. So finding this asymptotic nature is facilitated by the generating functions. So I won't give a proof right now. In fact, even this paper doesn't give a proof of it. But for knowing the proof, you have to consult a different paper. I may put the link there. The main idea is actually use complex variables. So what you do is you take a generating function like this, and then instead of q, you replace it with z as a function of the complex variable z. And then you observe that this is nothing but a function f of z, and it is its representation as a Maclaurin series about z equals to 0, or Taylor series about z equals to 0. And then you know that nth derivative of f at the point z, it can be easily found out as n factorial by 2 pi I times the closed loop integral of f of z divided by z minus z naught. Here z naught is 0 itself, to the power plus 1 dz, where c is any closed contour about the point z equals to 0. So from there you will find fn of z, because you already have f of z, which is this thing. So you put it there, you will find out nth derivative of f at the point z, and that thing times n factorial. So n factorial times fn of z at the point 0, I'm sorry. Nth derivative of f at the point 0, this thing is nothing but this MD of n. However, this is said easier than done. Firstly, this function itself is a very wild function, and finding its and to compute this closed loop integral, you have to, there will be many functions, and the functions have various orders of poles at z equals to 0, and finding the residues, and then you have to perform some super non-trivial messaging with the quantities obtained, and then only you can find out the asymptotic behavior, which is very non-trivial, in fact. But the main idea is this, that you have to find out the residues of the functions which are in product at z equals to 0, and then find the infinite product, and then that will help you to find out what will be the asymptotic behavior of MD of n. Of course, you have to take a limit of large n and then see how it goes. And from there, you can essentially prove this thing. But log MD of n, but MD is nothing but the numbers generated by McMahon's generating function. So we know that M1 of n is P1 of n. I mean, M2 of n is P2 of n. I mean, they are the normal partition functions in 1 and 2 dimensions, but M3 of n is not equals to P3 of n. Because this partition function conjecture of McMahon holds only for d equals to 1 and 2. For d greater than equals to 3, it doesn't hold. So this asymptotic behavior is true for d equals to 1 and 2, where MD can be replaced with PD. It's a fairly difficult asymptotic function, as you can see. So you have to do lots of non-trivial work with these things, but yeah, you will get a Riemann zeta of d plus 1 also. So yeah, you have to do some non-trivial stuff with it. But that's the main idea how you get the generating functions. Now, the fact that generating functions don't exist for dimensions greater than equals to 3 poses a problem even to find out the asymptotic behavior. Because you don't have a generating function, you can't do all those complex variable tricks. And so the only way you can find the asymptotic behavior is to perform a Monte Carlo simulation of the partition function for large n, and then look at the asymptotic behavior by fitting it to some polynomial. And this will be goes as, yeah. And for d greater than equals to 4, we don't yet know what will be its asymptotic nature. For d equals to 3, this asymptotic nature was found out to be this uh, using Monte Carlo simulation, and the asymptotic nature, I mean, it is given like this. Why do you have plus minus? Because it's a Monte Carlo simulation, so there are statistical errors associated with the various coefficients, and this is how you get it. Now you may ask that, well, how did we know that that the asymptotic function will have these coefficients of n? Well, this is because that there is a result by I don't know the author, maybe Bhatia, that for any PD of n, the terms in the asymptotic function will consist of n to the power d by d plus 1 all the way to n to the power 1 by d plus 1 log n and some constant term like this. But what will be the coefficients of those terms? Those terms we have to find out using a Monte Carlo simulation. And it has been done for 3D. We don't yet have any idea about how this asymptotic function looks like in d greater than equals to 4. It's still an open problem. Yeah. So now let's come to partitions inside a hypercube. So till now we were talking about partitions which are unrestricted. And yes, we also talked about restricted partitions in the sense that we also talked about partitions of n such that you have in many parts and so on, that sets up a restriction on the partition. But apart from that, we were talking about unrestricted partitions. So now we will be talking about a very interesting class of restricted partitions, which is partitions inside a hypercube. Well, before that, till now, I don't know if I was fast or maybe too slow, but if you have any questions, you can ask. In case if you have some, or if you haven't understood anywhere, you can ask me. Am I in the meeting? Am I audible?
Yes, yes, you are audible. Yeah.
Okay. How the things isn't working right now. I hope it's okay. I haven't tried MS Teams in this device anytime before, so I'm not sure. Okay, so let's get into partitions inside a hypercube. So to motivate it, let us consider a 2D partition. Let's consider a one-dimensional partition. Its Ferret's diagram will be in lattice plane Z2. It will be, well, I haven't yet, I'm just drawing the lattice plane right now. And so much it extends in all the directions. Now consider a box in the lattice plane. Let's say 1, 2, 3, 4, 5. 1, 2, 3, 4, okay, 4. And consider the partitions of n that fit inside the box. That is all the Ferret's diagram of this partition n, which are contained inside this box. Maybe this will be an acceptable one. Let's say n equals to 1, 2, 3, 4, 5, 6, 7. But of course, this one, 3, 5, 6, 7, this is not an acceptable one because these two entries get outside the box. Okay, so we shall focus on all those partitions of n let's say here one-dimensional partitions of n that can be fitted inside the box of length 4. So in this object, these black ones that I showed later will not be an acceptable entry, but the green ones that I showed before will be an acceptable entry. And this idea can, of course, generalize in D+1 dimensional Ferrari diagrams for D-dimensional partitions. And that's what we have here. So PDLM denotes the number of D-dimensional partitions of n whose Ferrari diagrams can be fitted inside a hypercube of volume L to the power D+1. This square has a volume, for 2D its area of L square, and this will have a volume of L to the power D+1 for a D-dimensional partition. Clearly, this object is 0 for n greater than or equals to L D+1 because this box can at most hold L to the power D+1 points in D dimensions. Like in 2D, it can hold L square points. And if n is greater than or equals to this L to the power D+1, that is n is greater than or equals to n greater than LD+1, then no partition of n can be fitted inside the box. So it will be 0. And this is an important bijection, that this object is equal to this object. Why? This is because if you consider a Ferrari diagram like this, a 2D Ferrari diagram of a number, which is, let's say, which is inside a box of size, say, 5. And we have this Ferrari diagram, this. Then the complement of this box, which consists of these many points, when you view your axis like this, x1 prime, x2 prime, let's say, then the complement also serves as a Ferrari diagram. So if this is a Ferrari diagram, then its complement inside the box, which is this object, is also a Ferrari diagram. So for every Ferrari diagram of n, there exists a Ferrari diagram of n to the power D+1 minus n. And equivalently, for every Ferrari diagram of L to the power D+1 minus n, if you see the box from this viewpoint, there exists a Ferrari diagram of n. And again, this is a bijection, a Ferrari bijection, the one that I talked about earlier. Well, here we aren't doing any sorts of transformations, but graphically, diagrammatically, you can see that there exists a bijection. And this shows that these two are equal. Now, the next is an important conjecture. It says that PDL of n as a sequence of n is unimodal for every natural number d and n. It means that this sequence n for n belonging to natural numbers, this sequence is unimodal, which means that this sequence is increasing, which is the maximum, and then it decreases. And of course, for n larger than e to the power D+1, it is identically equals to 0. Okay. So unimodality means that it has only one peak, or it cannot have any other undulations anywhere. It is mechanically increasing and then it decreases off and finally it goes to 0. That's what unimodality means. And it is proven for d equals to 1 and 2. But in higher dimensions, it still remains a conjecture that needs to be proven. Although it is widely accepted that it is true, because we haven't found any counterexamples so far. Now, for partitions inside a hypercube, we have this identity. And so to understand that, first we have to understand what we mean by Dedekind number. What is the Dedekind number? So to understand Dedekind numbers, so this is a digression. First, you have to understand what do you mean by a Boolean function. So a Boolean function f takes in n many inputs, either 0 or 1. So Boolean function f of n variables takes in a Boolean input that is either 0 or 1 and gives out output which is also a 0 or 1. So it takes in 0, 0, 0, 1, 1, 0, 1, let's say, and gives out either 0 or maybe 1. That's what it means by a Boolean function. So if we have so how many Boolean functions do we have for n variables? So the number of such functions is equals to 2 to the power 2 to the power n, as you can easily see, because there can be 2 to the power n many combinations, and for each of 2 to the power n combinations, you can have two outputs, right? So these 2 to the power n combinations can be mapped either to 0 or 1. So 2 for this, for each 2 to the power n, so it is 2 to the power 2 to the power n. And you can easily observe that this will be an extremely rapidly growing number. Even for n equals to 5 or 6, it can just be very, very large. And now, what do it mean by monotonic Boolean function? Of n variables. So a monotonic Boolean function of n variables, what it does is, what that function is, that let's say we have a function here, and that is equals to, let's say 1. Now, if any of these entries now become 1, let's say this 0 is now changed to 1, and if this, and for this, if this 1 becomes 0, then this is not a monotonic Boolean function. This is not allowed. So formally speaking, if any of these entries, if f is x1 to xn, and if any of these entries xi, which was previously 0, and if it changes to 1, then the function can change either from 0 to 0, that is, it remains unchanged, or 1 to 1, or 0 to 1. But it cannot change 1 to 0. That is, the value of the function cannot decrease in some sense if any of its arguments are increasing in some sense from 0 to 1. Okay, so these are the allowed operation. These are the allowed values of the function for some xi from changing from 0 to 1. And such functions are called monotonic Boolean functions. Now, well, you have a closed form solution, closed form number for the number of Boolean function in n variables. But the number of monotonic Boolean function in n variables, we don't have any closed form answer, any combinatorial answer in terms of n choose r or factorials or something. And again, it is an open problem. So, but perhaps mathematicians know that we can't have a closed form solution for the number of monotonic Boolean functions. And this is a special name. This number of monotonic Boolean function is called the Dedekind number, the nth Dedekind number, because it was first, the idea was first given by Dedekind. And interestingly, we have found that if I take all the possible partitions, if I take all the possible partitions of n that can be all the possible partitions of n that can be fitted inside a hypercube of volume 2 to the power d plus 1, then the number of all such possible partitions gives you the d plus 1th Dedekind number. In fact, this wasn't analytically proven first. What people did is they first computed the left-hand side, and interestingly, they found that for b equals to 1, 2, and 3, maybe they are reproducing the Dedekind numbers. And then they thought that, well, there must be some sort of connection between, and then this relation was formally proven. The proof of this relation is also very beautiful. I think I have time. Okay. So the proof is as follows. The proof is due to Suresh sir. The proof is as follows. what you did is you take the main idea behind the process as follows. Let us, for the aid of visualization, I'm taking d equals to 1 for now. I mean, it can be distributed to any number of dimensions. And consider a partition. You can consider all these points inside this box. It's a 5 × 5 box, let's say. So the number of entries inside, so the number of points that you have inside is 5. Oh, I'm sorry. I'm sorry. I have to take box of dimension 2. Yeah. So the number of points inside is 2 to the power 2. And if this point belongs to a Ferret's diagram, then this point will be 0. And if this point doesn't belong to a Ferret's diagram, this should be 1. Well, let's see this one. Let us do it in this way. Consider a Boolean function f of 2 variables. Let's say the function be being 0 and 1, giving you 0, f of 1 of 0 gives you 1, f of 0, 0 gives you 0, and f of 1, 1 gives you 1. In that case, this point 0, 1 will be this point. This f of 1, this f of 0, 0 will be this point. Sorry, f of 0, 1 will be this point. Well, it depends on which you take x-axis, y-axis. Let's say this. Now you can see that this is a Ferret's diagram. You can easily see that this is a Ferret's diagram because, in fact, this is a partition of 2 that can be fitted inside a box of length 2. And interestingly, this function is also a monotonic Boolean function, as you can easily see. So every monotonic Boolean function f can be mapped bijectively to a Ferret's diagram inside a box of side length 2. And this can be extended to any higher number of dimensions. The design is very simple. Well, the mapping is very simple. What you have to do is, if you have a point, let's say 0, 0, 1, 0 plus 0, a Boolean function of 5 variables. So this corresponds to a point in 0, 1, 5, which is again a point inside the 5-dimensional Ferret's box. And if this is equals to 0, then you associate that point in your Ferret's diagram. That is, you take this point inside your Ferret's diagram for the corresponding partition. And for all those entries where the function evaluates to be 0, you take those points inside your Ferret's diagram. You take those points inside. And now you see that for that function f, do those points satisfy Ferret's diagram? That is, do those points satisfy the weakly decreasing criterion? If it does satisfy, then you are guaranteed that this function f will be a monotonic Boolean function. And the reverse also works. In fact, the proof of this is the fact that, in fact, I think you can prove it very easily yourself. I can't explain it right now more clearly, but the proof is the fact that if lambda is a partition, then all the points in the partition, you take all the points in the partition and take them to be 0, if x belongs to the partition, and 1 if x doesn't belong to the partition, then this f of lambda will be a monotonic Boolean function. And if you do the reverse, that is for every monotonic Boolean function, you can associate a partition, then this f lambda will be a bijection, and you can easily show that this is indeed a bijection. And this is the way in which we actually show this, that this relation is true. Again, Dedekind numbers are computed till I think up to d equals to 8. Up to d equals to 7, it was computed in 2014 or 13, I guess, and M8 was calculated just a few months ago in 2023. Okay. Again, it is an extremely computational intensive job, and in fact, after this partition identity was proven, the standard way of computing the Dedekind number became this. So what people began to do is they began to enumerate all the partitions that can be fitted inside a box of length 2 in d+1 dimensions, and they enumerated all those partitions, found out the number of partitions, and that was the Dedekind number. And there are many clever algorithms which do it. I think Wiedemann's algorithm is it is the algorithm that was used to compute d equals to 7, and an extension of it was used to compute d equals to 8. But again, it becomes extremely computationally intensive, and computing Dedekind numbers for d greater than equals to 9 is an open problem right now. So in fact, when I joined this project first, I joined this project very recently. I first thought that, well, I will try to find out an algorithm to compute d greater than equals to 9. But then Suresh sir said that it may require some, it will be an extremely difficult job. So he rather told me to concentrate on this problem, which is also still a very less understood problem and comparatively new problem, and that is partitions inside a simplex. So we talked about partitions inside a box. Partitions inside a simplex is just a different version of it. Like box is one geometrical object, simplex is another. Simplex is essentially the generalization of triangles and tetrahedra in two arbitrarily large number of dimensions. And this definition essentially shows the fact that a Faraday's diagram that can be fitted inside a triangle. This is a simplex of dimension 2, let's say. Similarly, this is a simplex of dimension 3. And if you actually put this tetrahedron in a way that these three edges are along the three coordinate axis, then this plane will actually satisfy the condition that x1 plus x2 plus x3 is equals to some k, where k is some estimate of the size of your simplex. And this can be estimated to any number of dimensions. And now the problem is again the same problem. Compute the number of Faraday's diagrams that can be fitted inside the simplex. But although the problem is same, but the algorithm that is needed, I don't know still about what algorithm we can use. I have a faint idea in my mind, but it's not very bright. I have to work on it. But so my idea is to use the same algorithm that is used to calculate partitions inside a hypercube, and somehow modify it so that it works for simplex. But I don't think it will work, or it may. I'm not sure. And still, and as is the case with higher dimensional partitions, we just have a closed form solution for a triangle. That is for 1D partitions that can be fitted inside a triangle. And this you can easily prove actually. These are the Catalan numbers CN. And but for partitions inside a tetrahedron or higher simplices, I don't have any idea, and it's still an open problem. And moreover, the bounds, well, we have an estimate on their bounds. Very recently, someone found out that the partitions inside a simplex do have a lower bound and upper bound, but their asymptotic behavior, etc., are not still properly understood. And I hope I will try to I hope I will be able to shed some light on. I mean, if I can enumerate the partitions inside a simplexes for large enough dimensions, we shall have an idea about what its asymptotic behavior can be. And maybe then we can find some Monte Carlo simulation to find out its asymptotic behavior and so on. And yeah, that's what concludes here. Do anyone have any questions or anything they can ask? Sure, why isn't it? Is everyone with me right now? Am I audible?
Yeah. So if no one has a question, I'll stop the recording now.
Yeah.